Welcome to a lesson with Dr. Powell. Let's take a look at a way that we can compute the characteristic polynomial of a matrix, this one right here, without actually going through the whole determinant finding process overall. Okay, we're going to do this one term at a time. The result will be over here, and we'll have to modify it a little bit sign-wise from what we're doing over here. What we do is we kind of pinpoint things. First of all, x cubed is going to be the leading term. It always is for characteristic polynomials. We always have, in this case, for a 3 by 3, we have 3 x's going down. It's going to be x cubed. There's no other way to get an x cubed term, just 1. We're always going to have a plus 1 times x cubed. That means it's monic. A monic polynomial is one where the leading coefficient is plus 1. All right. Next, what are we doing? Let's look for the coefficient of x squared. How would we do it? Well, as we go down, so notice what I've done is I just took the matrix itself and I just added x down the diagonals. Instead of saying like x minus everything, we just said x plus down the diagonal. So this is kind of like the characteristic polynomial, but not really. What it is, it's kind of like plus or minus what's happening because really what's happening if we don't multiply this matrix by negative, we're not multiplying it by this matrix like -1, -1. Okay, then actually determinants determinants are multiplicative, meaning that the determinant of this matrix, which is -1, multiplies to this one if we've multiplied it by a negative. So now in the 3 by 3 case, I guess we're multiplying it by a -1. In a 4 by 4 case, we'd just be multiplying by +1. So that would be okay. So it's kind of, there's a couple changes, and we also are like we're plugging a negative x in. It's going to mess with the signs a little bit, but we're going to get that straight. We're going to ignore this right now because there's a simple way to get around the signs. So we're just going to look at this simple case. Really, that's just motivation to say that this suffices just to consider what we're doing here. In fact, in general, we don't even have to write these down, but we're doing this only for instruction right now. How would we find x coefficient of x squared? Now, computing a determinant, it's like computing kind of like skewed or messed up diagonals where like you have like this guy, this guy, this guy, or you could go this guy, this guy, and this guy, things kind of like, as long as you never use what's in the same column or row, you're fine, okay? But we can also so you can kind of think about it that way, and you're adding up these products. Now, notice that as we go with these products right here, we're not mixing it up right here for the coefficient of x squared. We're just going straight down the diagonal. So we don't actually change the sign on any of these diagonal multiplications. Really what we're doing is we're just distributing within the diagonal itself. Notice that we have to have 2 x's. So that means we've used an x here and maybe an x here, but that actually tells us that we have to be on the diagonal again. This diagonal again in our calculation of the determinant when we're multiplying things up and adding them up. So in this case, the only ways of doing that is we have 2 x's from here, then a 2, or these 2 x's and a 1, or those 2 x's and a 1. So really we're just adding up these. It's 4x squared. It's kind of like, actually, it's called the trace of a matrix. You simply just add up what's down the diagonal, and that's going to be this guy right here. So the term that's 1 down from the leading is the trace. Now, in general, what we do is we take the trace and we actually change its sign, because what we're going to be doing is the numbers that we find, we're going to go down and we find them and we put them on, and then we go down in a plus minus fashion to whatever we find. Okay, so in this case, we get a 4, and we could have easily gotten that just by adding what's down the diagonal. Now, how do you find the coefficient of x? Okay, we're only going to be using one of these guys at a time. So if we use this one, then what's left over? Just what's kitty corner to this. So those guys, but we can't use any more x's. So it's like it's this case right here. So we can only use that. So basically, we're just finding we're finding the determinant. In fact, even the cofactor, if you will, in this case. Notice that the x is down the diagonal. If you think about a checkerboard pattern for the matrix, the diagonal always has pluses going down, which is kind of nice if we're working off of the diagonal, which we will in this case. In fact, for all these coefficients, that's really what we'll be looking at. All right, so let's proceed here and see what we get. So we have this x, we have that matrix, we have this x, we have that one, this x, that one. So we're just pretty much summing up the cofactors that happen down the diagonal of the matrix. And we compute this determinant. So 2 minus, so we have 2 minus 3, which is -1. This guy we have 2, so we have 2, and then we have a +4, so we get a 6. Here we get a 1 minus 0, so we just get a 1. We add these up, we get 6x. -x plus 6x plus x is 6x. So that's the term right there. So we'd put it right here. Then going down in our plus minus plus fashion, it still remains as 6x. Okay, now how do you get the constant term? It's just the determinant of the whole matrix because we're not using any of the x's. It's the only thing to get a constant, which is just the determinant of the whole thing. We can do a cofactor expansion on this first column. So 1 times what's kitty corner plus 4 times what's kitty corner right there. And we end up getting 27. And then of course we have the plus minus plus minus. In this particular case, we actually, yeah, we had all those guys as being positive, but yeah, nonetheless, we just put the plus minus in afterwards. Okay, and that's the characteristic polynomial. Let's look at another example. This time, let's fill it in as we go. We know the characteristic polynomial is going to be x cubed, x squared, x, and then a constant. All right. Now we can fill in this one. First of all, it's a +1. It's always a +1. We're going to start with plus, and then here is going to be a minus, plus, minus, whatever we fill in to these blanks here. So x squared should be easy to get this one. We just simply add what's down the diagonal, which is -1. We're getting there. Now we look at this guy, the x. Let's see, what do we do for that? We go down the diagonal, looking at so we go down the diagonal right here, looking at what's kitty corner to each position. All right. So this 0, we think about what's kitty corner to it. This determinant, which would be 0, and then minus a -2, so it'd be a +2. So we're going to get a 2 from this position. Then look at this guy. So we have this determinant, that minus that looks like 0. So we get a 0 from that guy. From this guy, we also end up getting a 0. Well, that's good. We're getting pretty close. Then the last one is just the determinant overall, which let's just do a cofactor expansion on this column. So it'd be, this is in a negative position, so it's just negative times the determinant what remains. So that's -1 times, and that looks like 0, and then minus a -2. So that would be a +2 right there. And so we end up getting -2. So we put a -2 right here. And then we just sign adjust. So we end up getting x cubed. So we end up getting so x cubed, and then we have plus x squared plus 2x plus 2. And that is our characteristic polynomial. Thanks for watching.